Namaste and welcome back to yet another lecture on mathematical foundations for machine learning. We have been looking at the ideas of linear transformation. We wanted to figure out how to get the standard matrix associated with a linear transformation. Given a transformation T, we want to find out how to get this transformation, the matrix representation of this transformation. Suppose we have a linear transformation T which is going to say map from a vector space V to another vector space W. We said that this transformation can be captured in terms of a matrix. So the question is, how do we get the matrix associated with the linear transformation T? So that will be the focus of this lecture, and we will also look at some of the properties of linear transformations, and then we get into the idea of eigenvalues, eigenvectors. Okay, so let us get going. In the last class we looked at this example. We had let us say we had this transformation T which was basically taking any vector say in R2 or to another vector in R2 where the mapping was given by, you had a 2 component vector x comma y where the transformation results in a vector whose components were basically the sum of the 2 components of the input vector. The first component was the sum of the 2 components of the input vector, and the second component was the difference of the first component and the second component of the input vector. So we were able to get a matrix, and we stopped with the question, like, is it always that you transform from Rn to Rn, or can we have a transformation which will map from Rn to Rm or any vector space V, because we started saying that linear transformation is a mapping from a vector space V to a vector space W. So how do we get to the matrix of this linear transformation? So that is a question that we are going to ask. So let us go ahead. So obtaining the standard matrix associated with a linear transformation. What we will do is we will again take some simple examples in case of R2 to R2, a mapping from R2 to R2 itself, and then we will extend this idea to any Rm to Rn. So I am going to take some examples. Let us say example 1. So what I am going to do is, here you go, I have a transformation T which is going to map any vector xy in, basically this is going to be a vector in R2. This is going to map every vector in R2 to the origin, right. Now what does this mean geometrically? That is interesting to see. So I have this, let us say my standard R2, my xy plane with x coordinate say x and then the y axis. So what does this guy say? This says, look, I am going to take any vector and every vector in the xy plane. The transformation is going to be such that it is going to take every fellow in R2 and then map it to the 0 vector. So this is going to be my, let us say, domain, and this is going to be my range. So what is the range? This is what I am going to have. So the range is, so basically it is a mapping from, again we know that the domain is also R2, the codomain is also R2 in this case. But what is the range? Every vector in R2, this transformation T is going to map to the 0 vector. That is pretty interesting. All the infinitely many vectors that you have wherever, be it x axis, be it on the y axis, negative this, negative that, anywhere here, anywhere here, anywhere here. What is this transformation going to do? This transformation is pretty interesting. It says, look, you give me anybody, I am going to map here. right. Everybody, every vector here is going to get mapped to the 0 vector there, right. This is what we have. Now how do we get the matrix corresponding to this particular transformation? So the basic idea is, you know that the vector xy in R2, this vector x in R2 can be expressed as a linear combination of the standard basis which says x into 1 0 plus y into 0 1, right. This is the basis expansion in terms of the standard basis. You have your 1 0 and 0 1, basically the I mean what you call as the E1 vector and the E2 vector, that is the standard basis for R2. We know this. Now what does the transformation do? The transformation is an interesting fellow. He takes every vector xy and he is going to give me 0 0. That means I am going to write this as, since the transformation is going to be linear, I am going to write this as t of x1 into 0 plus y into 0 1 is going to be t of, this is going to be x times t of the transformation that it does to the 1 0 vector plus y times the transformation that it does to the 0 1 vector. Now what is the transformation of the 1 0 vector? It goes to 0 0, the origin. What is the transformation of this vector 0 1? That also goes to origin. The transformation itself says, look, any vector you give me, I am going to map it to the 0 vector. Therefore now what I am going to do is, I am going to have the matrix form of this. The matrix form of this is basically the transformation of E1 vector and the transformation of E2 vector. Now what is it going to do? Transformation of E1 is basically 0 0 and that is going to be 0. Therefore the matrix associated with this transformation M is going to be this. Yeah. Let us take another example. Example 2. Let us consider a transformation which is going to map, let us say R2 to R2 such that this fellow takes every vector x comma y in R2 and he is going to give me this vector y x, right. It is going to give me the vector y x. So what does that mean? Let us look at this. So again let us look at what the transformation does to the standard basis and then we will figure out what it is. So what does this do? Transformation of the 1 0 vector is going to result in 0 1 and the transformation of the 0 1 vector is going to result in 1 0, because whenever you have x comma y, the transformation results in y comma x. So this is what we have. Therefore the matrix associated with this is nothing but, as we said before, transformation of 1 0 vector and transformation of 0 1 vector. So I am going to get 0 1 1 0, right. This is pretty interesting. What does this guy do? This guy is basically going to swap the rows of the 2 rows of a 2 component vector, and that is one of the operations that we actually do in elementary row transformation, right. We do row swap, right. When we say R2, for example, in obtaining the row reduced echelon form, obtaining the row reduced echelon form of a matrix, we may want to swap rows, right. We may want to swap rows. And when you say we want to swap rows, that gets done or that gets implemented as a matrix operation. So the corresponding matrix is basically this matrix 0 1 1 0, which basically this does R2, or let us say R2 is, it swaps R2 with R1 and R1 with R2, right. Let us also see what it means in a couple of minutes. I am just going to write a couple of more transformations of this sort and then let us see what it means, right. Okay. So what does geometrically this mean? We already know it. So we have, let us say x1 x2 x3, it means you have your x axis, you have your y axis, and we have this So, let us say 1 2 3 4 1 2 3 4 and 0. Now, what it does, this particular transformation, it takes, let us say it takes the vector 3 comma 2, this is the vector I give 3 comma 2 as the, this is the vector to be transformed, or this is the vector which is going to undergo this transformation, let us say t of x comma y, which is equal to y comma x. So, 3 2 now becomes actually 2 3. That means it actually says, look, I have put a mirror here, y is equal to x, which is going to reflect this point 3 2 to 2 3. So, this is basically the transformation essentially is a reflection about y is equal to x line. Right. Let us take another one, another example. So, let us take this as example 3. Again I have, in all these cases assume that I am going to have this transformation which is going to map from R2 to R2, right. In all the cases this linear transformation T is going to map from R2 to R2. So, the example that I am going to take now is basically the following. T is basically, it maps any vector x y, it maps to, let us say minus x y, right. It maps any vector x y to minus x y, that is pretty interesting. So, what does that mean? Let us again check what it does to the 1 0 vector, the transformation of the 1 0 vector. What is this transformation going to do? Whenever I have any x component, that x component is going to change to minus x. So, I am going to have this, and y component is retained as this one, and transformation on the 0 1 vector, this is going to remain the same because 0 is minus 0 is going to be the same. So, you are going to have this as 1. Therefore, the matrix associated with this is minus 1 0 and 0 1. Now, what does this do? This simply means, look, I have some vectors here, I have some vectors here, here and so on. What it does is the y component, the y value remains the same. So, what it does is it basically moves here, this point here with the y value remaining the same, this guy goes here, y value remains the same, this guy goes here, y value remains the same. That means whatever you had, let us call this as like 1 2, let us call this as let us say 2 3, and let us call this as let us say 3 4. Now, what has happened? 1 2 has become minus 1 2, 2 3 has become minus 2 3, and then 3 4 has become minus 3 4. That means it looks like I have kept a mirror along the y axis such that it reflects. So, this is going to be a reflection along or reflection about the y axis. Now, can I do a reflection about x axis? Of course, I can do. So, the matrix is going to look something like this, or the transformation is going to look like this. It is going to take vector x comma y, and then it is going to map to say x comma minus y, x comma minus y. So, what is going to happen? I am going to have t of 1 0, t of 1 0 is going to remain as 1 0, and then the transformation on the vector 0 1 is going to give me 0 minus 1, which means I have this, let us say I have these points, and let us say I have these points, I have all these points. Now, what it does, this transformation, this is going to be under the effect of this t, whatever t that we have written here. So, this is also this is also here. So, what is this transformation going to do? This is interesting. This point is going to come here by a reflection, this point is going to be here because the x value is the same, but y value changes. This is going to be okay, this is going to be somewhere here and so on. So, this guy is going to be here, this guy is going to be here, and that guy is going to be somewhere here, right. X coordinate is the same, and then the y coordinate changes. Therefore, the matrix corresponding to this t, we can actually put it as m of t, which is nothing but 1 0 0 minus 1, right. This is reflection about the x axis. So, now what happens is, like, given any mapping, now I am in a position to figure out the matrix that we have the matrix associated with the transformation is something which we can get. So, we also stopped with a very interesting question in the last lecture. We said that is it always that you are going to map let us say from R2 to R2, are we going to map from R2 to R any other R3, R4, can we do something like that? If that is the case, what is the matrix that we are going to use? That is a question that we had. So, let us take some examples of that sort. Okay. So, we can actually look at contraction, dilation and all those things in R2. You have matrices associated with even those guys. So, that is pretty straightforward stuff, like you know what the transformation does to the basis in terms of contraction, in terms of dilation, in terms of let us say rotation, you can actually figure out all that, right. Now, what I am going to do, I am going to look at two different vector spaces now, right. So, I am going to look at this, let V be equal to let us say R2 and W be equal to R3, right. I am going to define a linear transformation here T, which is going to map every vector let us say x y in basically in V, it is going to map to let us say this x, let us say x plus y, and let us say I have y, right. I am going to do this mapping here. So, the question is what is the matrix that is associated with this particular transformation, and in turn we will look at something more. So, can we find a matrix which does this transformation? So, again we have the same business, let us look at what the transformation does to the vector 1 0. The vector 1 0 of R2, which is basically one of the elements of the standard basis, is going to get mapped to this. What is the first component of the resultant vector? The 3 component vector. The first component is the same as the first component x here. The second component is going to be the sum of the 2 components of R2. So, I am going to take it as 1 plus 0, which is 1, and the third component I am going to retain my y axis or the y component as such. So, this is going to be the transformation of 1 0 results in this vector 1 1 0. And let us see what happens to the transformation of the vector 0 1. Transformation of the vector 0 1 is going to result in, let us say x is going to be retained as 0, x plus y is going to be 1, and y is going to be retained as y. So, this is what we have 0 1 1. Therefore, what is the matrix which is going to do this transformation? The matrix is going to be 1 1 0 0 1 1, right. This is what the matrix, this is the matrix that is associated with this transformation T, which takes every vector in R2 to a vector which is of this form x, x plus y and y in R3, right. Now, can we generalize this further? Let us take another example. Let V be R2 and W be R3 itself. Now, where I am going to define the transformation in such a way that it is going to take every vector x y and it is going to map to a vector which is of this sort Ax plus By, or let me put it in a different way. I am going to have this, it is going to do this A11 x plus A12 y, A21 x plus A22 y, A31 x plus A32 y. So, what am I going to get? I will check what is it going to do to my transformation. I mean, what is it going to do my basis vector, the standard basis vector. So, this is going to be T of 1 0 is nothing but A11 into 1 plus A12 into 0. So, I have A11 into 1 plus A12 into 0. We have A21 into 1 plus A22 into 0, and then we have A31 into 1 plus A32 into 0. which is going to be A11, A21, A31. So, the 1 0 vector is going to get mapped to this vector A11, A21, A31. What about this vector? This vector 0 1 is going to get mapped to A11 into 0 plus A12 into 1, A21 into 0 plus A22 into 1, A31 into 0 plus A32 into 1. So, this vector is going to be the transform vector, or the transformation of 0 1 results in this vector A21, A22, A23. Therefore, I am going to have this. So, the matrix associated with this transformation is going to be the transformation on E1 and the transformation on E2. So, these two we are going to put it in a matrix form, and we are going to get A11, A21, A31, A12, A22 and A32. So, this is the matrix that is associated with transforming every vector in R2 to a set of vectors in R3. Of course, there is a question that comes here, it is R3, does every vector in R2 get mapped to all possible vectors in R3, right? There is a problem here. So, the question here is, does T map entire R2 to entire R3 or to the whole of R3? That is pretty interesting. Does T map entire R2 to entire R3, right? Okay. We will come back to answer this question in a bit, but let us take one more example and see like what happens. Okay. Let us take one more example. So, let us take another example before we get to answer this question. Example. Okay. Let us take this. I have this, let us do this probably. I am going to have a vector space V, which is going to be R3, and I am going to map this to W vector space, which is let us say R2, right. So, I have a transformation T, which is going to be a mapping between R3 to R2, and so what does it do? This transformation is going to take this vector x1, x2, x3, it is going to give me a vector which is let us say x1 plus x2, and I will retain this guy x3, right. I want to look at the matrix which is associated with this transformation. So, how do I do this? I will do the same business that I have. What is the business? I am going to check E1, E2 and E3, because it is a 3 dimensional vector space. I will have 3 vectors in the basis. So, you are going to look at the transformation on E1, what the transformation does to 1 0 0, what is the transformation that you have on this vector 0 1 0, and what is the transformation on this vector 0 0 1, right. We need to study this. So, let us rewrite again. So, it is going to take T of, the transformation is going to take a 3 component vector, and it is going to give me 2 components vector such that x1, x2 and x3, this is the vector that I get. So, what is T of 1 0 0? T of 1 0 0 is 1 plus 0 is 1, and this guy is already 0. T of 0 1 0, that is going to be 0 plus 1 is 1, and the 0 is retained as such, and T of 0 0 1, what is that going to be? It is going to be 0 plus 0, which is 0, and this guy is going to be 1. Therefore, what is the matrix that is associated with this? The matrix associated with this is basically 1 0 1 0 0 1. So, what does this do? This matrix, if you see, is going to take any vector. This is what we had, right. So, we can very clearly verify this. This matrix is going to take any vector of the form x 1 x 2 x 3 and results in giving it is a 2 component vector which is x 1 plus x 2 and x 3, right. That is the most important understanding that we have here. Now, it looks like in this case, so we again ask the same question. What is the question? Does T map entire R3 to entire R2? Right. Does T map entire R3 to entire R2? Now, let us go back to the previous example and figure out an answer for this, and once we figure out an answer for that, I think we will be able to get the answer for this question also. So, what is the previous example that we had? We had a transformation T which was going to take vectors in R2 to give me vectors in R3. Now, recall that when you have 2 dimensional subspace or 2 dimensional vector space, say for example in this case R2, I just need 2 vectors linearly independent which would in turn become the basis for R2. So, if I want to study the effect of this transformation on the entire R2, it is enough that I study the effect of transformation on any basis of R2, because every vector in R2 is going to be expressed as a linear combination of the basis vectors. It is going to have a basis vector, the basis expansion, and you can get this. Now, if you look at R2, R2 is basically a 2 dimensional space. R3, if you go, R3 basically requires at least, it requires exactly 3 linearly independent vectors to span the entire R3, right. We saw that in the first week lecture where we were talking about span and basis and stuff, and we said that the number of elements in the basis is going to be the dimension of the vector space that is spanned by the basis. Say for example, I have R3, W is R3, W is a 3 dimensional vector space, therefore, I definitely need 3 linearly independent vectors which would span entire R3. Now, if you look at R2, R2 just has 2 linearly, any basis in R2 will have only 2 vectors, linearly independent vectors. That means in R3 there is no way you will be able to, for this transformation T, it is impossible for you to span the entire R3, because in the last lecture we also made one nice statement. We said that look, any linear transformation is going to map a line to another line, a line passing through the origin to another line passing through the origin or to the origin. That means it preserves the dimension in that case, like let us come back to this. But if you look at this, when you go from a lower dimensional vector space to a higher dimensional vector space, now what is happening here is that R2 is going to be a plane passing through the origin. Naturally, this plane passing through the origin in R3 will get mapped to a plane passing through the origin or to a line passing through the origin, or it will get mapped to the 0 vector itself. Therefore, this transformation that you have T, which is going to map from R2 to R3, can at the maximum span a 2 dimensional subspace of R3, right. In the next case we see this is a very interesting example. The next one that we see, you have more information now in terms of R3, you have an extra dimension that is there now, and it is going to map to a vector space which has got only 2 dimension, that means the number of dimensions in in W vector space is 1 less than that of the dimension of the vector space V. So, you are basically moving from a higher dimensional vector space to a lower dimensional vector space. Now, we know that the basis here in R3 you have 3 basis vectors, I mean 3 elements in the basis, and if you look at the corresponding matrix for this transformation, this particular transformation, you could actually see that what would you call the vectors that you have in the matrix are all like 2 component vectors, and there are 2 of them which are linearly independent here, basically 1 0 and 0 1, the linear combinations of which will give the entire plane, the entire R2. So, in this case, in this example, the answer is yes, and in the previous case the answer in this case it is basically no, right. Okay. So, what are we trying to say? We are going to say that okay, if you are going from, see the point is like you are in case of R2 there are only 2 pieces of information which are going to be kind of coded in the 2 elements of a basis. R3 requires 3 pieces of information, you already lack 1 piece of information here. So, it is not possible for us to map from R2 to entire R3, whereas the other way is possible, because I mean that is what happens even in projection, you can go from a higher dimensional space to a lower dimensional space. So, you have R3, the R3 gets mapped to a plane or it gets mapped to a line, projection onto a line, projection onto a plane, or it is going to get mapped to the 0 vector itself, right. So, let us look at this. So, we already saw that associated with a transformation we have 2 important vector spaces or subspaces which we called as the kernel and the range of the transformation. So, recall there are 2 vector subspaces associated with any linear transformation, namely the kernel of T, let us say linear transformation T, kernel of T which is basically denoted as this. What are we going to say here? This is going to be suppose if T is a map from let us say V to W, that means V is a vector space and W is yet another vector space. If T is a linear map from or linear transformation is already given, it is a linear transformation from V to W, then there could be a set of vectors which will other than the 0 vectors, or it could just be the 0 vector which we know that in case of a linear transformation it is the 0 vector which gets always mapped to the 0 vector on the other vector space. But in addition to it there could be some more vectors which could get mapped to the 0 vector in the other vector space. Therefore, kernel of T is basically the set of x vectors in vector space V such that the transformation of x results in the 0 vector in the vector space W. Is that clear? So, the transformation of x vector results in the 0 vector in the W vector space. So, we are going to look at the set of all those vectors V's. Therefore, what we are going to say is kernel of T is a subspace of V. Now we also figured out, right, in the from the few examples we figured out that any linear transformation can be associated with a matrix. If you associate the linear transformation with a matrix, then what happens, the kernel is basically the set of all solutions to the homogeneous system of equation, let us say mx is equal to 0. So what do? Let us write this. We had already done this before, but just for the sake of recapping I am just doing this. We say that if m of t or m is the matrix associated with the transformation T, representing the action of the transformation on any vector, then the kernel corresponds to the kernel of T corresponds to mx is equal to 0, where let us say you have a the matrix M is an m by n matrix, assume that it is an m by n matrix which represents the transformation, and so corresponds to the solution to mx is equal to 0. That means we are looking for, we want the kernel of T. So here let us write this, the kernel of T is nothing but the solutions or the solution to the homogeneous system of equation mx is equal to 0. That means we are looking for x in Rn such that mx is equal to 0, but the 0 vector basically is an m component vector, right. We are looking at the set of solutions x in Rn such that mx is equal to the 0 vector in the the m component vector. So what is the vector space V here? The vector space V here is basically Rn, and the vector space W is basically the vector space Rm, right. That is what we have. The next one, the other subspace that we have here basically is the following: the range of T right. We are going to have the range of T, and this range of T is nothing but the set of all those vectors in W which can be expressed as, let us say which are the results of this transformation T on the vector, let us say, okay, let us do this. So range of T is nothing but the set of vectors that range set of vectors in W that are obtained by transforming the vectors in V by the linear transformation T. Now what does that mean? I am looking for the set of all those vectors W in W which can be expressed as, or which can be W in W such that T of V is equal to W, where V is an element of the vector space V. This is clear. So, this is called the range, and now that we associate a matrix with the linear transformation T, we will write, or we will try to express this in terms of the matrix case. So, what we will do is, suppose M is the matrix associated representing, or the matrix representation of T, then the range of T is given by the set of vectors let us say B in R M, which can be expressed as B is equal to A x for every x in R n. This is what it means, and essentially what we see is x's are all, these values of x are all going to be scalars multiplying the columns of A. Therefore, the range of the matrix, the transformation T, is also called as the column space of the matrix M. So, the range of the linear transformation T is also the column space of the matrix M. Right. And we already know that the dimension of the null space of the matrix is called the nullity of A, and the column space of the matrix, the dimension is called the rank of the matrix M, and that is associated with the linear transformation T, and the nullity of A is basically the dimension of the null space of the matrix M, where M is the matrix representation of the transformation T, right. So, these are some interesting stuff that we need to know, and I want to wind up the idea of linear transformations, the properties and all those things with just one more, and then we will look at eigenvalues and eigenvectors. I have been saying that we look at eigenvalues, eigenvectors for the last couple of classes, but we just wanted to put all these things together before we move there, right. So, let us look at this. What is that we want to do? Suppose let us say U, V and W are 3 vector spaces, and let us say T1 and T2 be linear transformation such that T1 maps, let us say U to V, and T2 is a linear transformation from, let us say, V to W, then we are going to define another transformation T, linear transformation T, which is basically the composition of let us say T1 on T2 or T2 on T1. So, let us look at this T2 T1, then T is a linear transformation from U to W, right. Let us look at this, let us see what that means, we will just do that now. So, let us consider this let this is something which we have done before, but we will come to it like what it means. Let us say u and v be elements in let us say u, right. Now I want to look at what is the linear transformation of u plus v. This is nothing but the transformation T2 applied on the transformation of u plus v, right, T1 of u plus v, which is nothing but T2 of, since T1 is a linear transformation, I am going to write this as T1 of u plus T1 of v. What does it mean? T1 is already a linear transformation that I have, T2 is also a linear transformation that we have. T1 is basically a transformation on the vector space u. So, it takes basically two vectors u and v in u. So, since it is a linear transformation, I am going to write T1 of u plus v as T1 of u plus T1 of v. Now, this is T2 is a transformation, linear transformation again I know. So, this is going to be T2 into T1 of u plus T2 into T1 of v, right, because T2 is also let us say T1 of u is going to give me say some vector let us say v1 in v, and T1 of v. So, basically T1 of u is going to give you, T1 is a mapping from u to v. So, this is going to give me a vector let us say v1, and that is going to give me a vector v2. T2 is going to operate on, so let us do this, probably one more step. Why will we not do this? Let us take one more step. So, we know that T1 of u is basically some vector v1 in the vector space v, and T2 of v is a vector v2 let us say in v, because T1 maps from, sorry, this is T1, because T1 maps from u to v. So, what do we have? We have T2 of T1 of u plus T1 of v is nothing but the linear transformation T2 applied on the vector v1 in v plus the vector v2 in v. Now, since T2 is a linear transformation, I can write this as T2 of v1 plus T2 of v2. I can write this as T2 of v1 plus T2 of v2. But what is v1 and v2? v1 and v2 are obtained as linear transformation of the vector u plus the linear transformation T1 applied on the vector v. So, what we have? We have T of uv, T of u plus v is equal to T2 of T1 of u plus v, which is equal to T2 T1 of u plus T2 T1 of v. That means you already get, you get the linearity property satisfied here. Let us take scalar multiplication and see if it actually works. Let us look at scalar. So, I want to look at the transformation applied on say some c vector c times u, scalar multiple of the vector u. So, I have this to be T2 of T1 of cu. Now, I know that T1 is a linear transformation, therefore, T1 of a scalar multiple of the vector u is nothing but scalar multiple of the transformation T1 of u. T1 of u is going to give me a vector in v, and therefore, transformation T2 is going to apply on a scalar multiple of a vector, say this is c. So, the T1 of T2 of c T1 of u is basically T2 of a scalar multiple in v, c scalar multiple of a vector in v, because that vector in v is obtained as a transformation of the vector in a vector u. So, what I am going to get? This is a linear transformation. So, T2 of scalar multiple times a vector is nothing but scalar multiple times the transformation. So, which means you have transformation of the scalar multiple is equal to scalar multiple times the transformation. Therefore, what we are going to do is we are going to say that therefore, T is equal to the composition T2 T1 is a linear transformation. Say for example, if T1 is associated with a matrix, let us say A, and then T2 is a matrix associated, I mean it has T1 has a matrix associated with it and we call it A, and T2 we have another matrix associated with it, we call it as B, then what we are going to say is the matrix that is associated with this T, which is basically the composition of T2 and T1, is going to be the matrix BA. That is what this means. So, matrix multiplication results in another matrix, and that matrix would correspond to another linear transformation, right, that is what we have. Okay. So, what are we going to do now? If you see here, like all these linear transformations that we do, we want to specifically look at a specific a case where assume that T is going to be mapping a vector in V to another vector in V, right. Both the domain and codomain are the same. The domain and the codomain for the linear transformation T is going to be the same. So, let T be again this goes without saying, T when I write it is actually a linear transformation. So, let us take it that way. So, T is going to be linear transformation which is mapping from V to V. Now, it could so happen that T could map a vector, for example, let us take this. I have a let us take this specific example where T is such that it maps a vector xy to, let us say, 2x plus y and x plus 2y. What is the transformation doing? The transformation is basically taking a vector in R2. So, I mean, I would say V to V, let me make this very specific here, let me make the vector space to be R2 to R2. Every action of the transformation is happening in R2, that means this guy is going to take a vector in R2 and is going to give me another vector in R2, right. What is the matrix associated with this? We already know what is the matrix associated with this, we can update it, we will say T of 1 0 is nothing but 2 into 1 plus 0, then we have 1 plus 2 into 0, this is going to get mapped to 2 1, and T of 0 1, the standard basis in R2, we have 2 into 0 plus 1 plus we have 0 plus 2 into 1. So, I am going to have 1 2. So, the matrix associated with this is basically 2 1 1 2. The matrix associated with this transformation is 2 1 1 2. Now, under this transformation that I have, I ask this question, what is that? Under the transformation T, which is given by, which is under the transformation T, which is represented by the matrix let us say M is equal to 2 1 1 2. Let us see what happens to every vector that I give. I will take very specific case of, let us say, the vectors and then see what happens. Let us look at the F vector, let us look at the effect of T. Right. What does this mean? I want to look at the effect of this transformation T on the vector 1 0. We already know this is going to give me 2 1. The effect of this transformation on the vector 0 1 this is going to give me 1 2. I want to look at the effect of this vector on, let us say, 1 3. This is going to be the transformation of, so what do I have? This is going to be represented by 2 1 1 2 into 1 3, which is nothing but 2 plus 3 5 and 1 plus 6 7, right. 2 into 1 plus 1 into 3 is 5, 1 into 1 plus 3 into 2 is 7. I am going to take some negative vectors. So, vectors with negative components. So, I am going to have 1 minus 2. So, what is this going to do? This is going to be 2 1 1 2 into 1 minus 2. I am going to have 2 minus 2, which is 0, and then 1 minus 4, which is minus 3. Let me try this transformation of this vector. Transformation of this vector, let us say minus 2 1, that is going to be 2 1 1 2 into minus 2 1, which is nothing but minus 4 plus 1, which is minus 3, and then we have 1 into minus 2 plus 2 into 2, which is 0. That means any vector that you give as an input to this transformation, the resultant vector seems to be thrown out into a different direction. The orientation of the resultant vector is different from the vector that got actually transformed. Is this right? Like the direction of 1 0 was along the x axis and 2 1 was somewhere else. The direction of 0 1 is along the y axis, but 1 2 is in a different direction. The direction of 1 3 is different and the direction of I 7 is different. So, what do I do now? I am going to ask a question. Given this transformation T, given very specifically with respect to this T, I am going to ask, given this transformation T, which maps every vector, let us say x y to 2x plus y and x plus 2y, does there exist, or let us say, do we have vectors in R2 such that this transformation of this vector x y, which is given by say 2x plus y and x plus 2y, results in some scalar times of the vector x y itself. So, what do we ask? We are given a transformation now, linear transformation, which basically maps every vector x y to 2x plus y and x plus 2y. We become a bit greedy. We want to ask, like, can we have vectors such that this transformation 2x plus y and x plus 2y, which is the, I mean, you given a vector x y, I mean whose components are x y, the transformation is going to result in a vector 2x plus y and x plus 2y. Can we ask for vectors wherein which the result of the transformation is nothing but the scalar multiple of the input vector? That means, can I have directions or can I have vectors for this specific transformation such that the transformation results in just scaling? The transformation does not change the direction, unlike the vectors here that we had. We took the vector 1 0 0 1 1 3 1 minus 2 minus 2 1. We took all these vectors, the direction seems to be going somewhere else. Now, what I want to ask is, I have the same transformation. For this same transformation, can we have vectors such that the input direction and the output direction are the same, or the input vector and the output vectors are the same, except that the output vector is going to be scaled by some factor, right. In a sense I want to look at what do we mean by this. So, let us look at a simple case, let us look at it from a different perspective. So, consider this, consider f of x is equal to let us say e power a x. Now, what I am going to do is I am going to take the derivative of this def by dx, I am going to get a e power a x. Let us look at d square f by dx square, a squared e power a x. What is this basically? This is the derivative of the function f of x, where f of x is nothing but e power a x, which we got as a e power a x. This is nothing but the second derivative of the function. So, this is nothing but d by dx of a e power a x, which we got as a square e power a x. Now, in this case that you see, for the differential operator that you have here, when you gave e power e x as the input, the output was the same function, but just scaled by a. Is this right? The function, original function was e power a x. Now, you took the derivative of this function e power a x with respect to x, the output is nothing but a scaled version of the input. You took the second derivative is also a scaled version of the input. So, you try to transform the function, there is nothing that changes except for the scaling factor. So, I want to look at something like that in terms of the vectors. Given this particular transformation, am I greedy enough, or am I really greedy to ask for direction such that you put this vector, you try to transform this vector using this particular, using this particular linear transformation. Is it possible to get vectors which get just scaled? We really do not know. So, what we will do is we will try to find out if such vectors exist for a given linear transformation. If it exists, then that is going to be quite interesting. If it does not, you are going to say like, yeah, it does not exist, so this the effort is going to be quite futile. So, what we will do is in the next class we will reconsider this transformation that we have here, which took every vector with components x y and then gave me another vector which is 2x plus y, whose components are 2x plus y and x plus 2y. For this particular transformation, we want to check whether this transformation can result in a vector which is thus the scaled version of the input. So, in the next class we are going to search for such vectors. If such vectors exist, we have some interesting result. If it is not, as I said, look, our efforts are futile, but anyway we figured out that look, there is no vector that exists this way, right, and that is where we are going to define eigenvalues and eigenvectors. So, we will look at that in the next class. Namaste.